Stripping down science. The Naked Scientists.
Hello, it's Sunday the 18th of December. Welcome to The Naked Scientists. I'm Chris Smith, and with me this week I have Helen Scales, Dave Ansell and Dominic Ford for a Christmas party. Hello, everyone.
Hello.
Now, this is our Christmas special, and we're going to be taking on your science questions, including what colour does a chameleon go, get this, when it dies? Why does water, but not salt, evaporate? And does antiperspirant deodorant actually make you sweat more? And also, will Brussels sprouts and why do Brussels sprouts make you sound a bum note sometimes on Boxing Day? We'll find out, Dave.
And in the news, we'll hear about a new camera that shoots 1 trillion frames per second, so fast you can watch a pulse of light moving across an object.
And how the reality of finding Nemo might be to not find Nemo. A new survey looks at just how endangered all the species are that feature in the Disney's film.
Plus, we'll be joined by Professor Carmodillo with a festive and musical take on the Higgs boson.
So, if you'd like to get in touch with any questions or comments, you can, of course, tweet at Naked Scientists. You can also write on our Facebook page, which is at facebook.com/TheNakedScientists, or drop us an email. Our email address is chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And we're off to a flying start. Luke is in Braintree in Essex. Hello, Luke.
Hello.
What can we do for you?
Is burning candles bad for the environment? And logic says it is, but why do we still burn them if it is? And also, is paraffin candles worse or better than wax candles?
OK, well, Merry Christmas to you. I suspect you'll be lighting up a few candles of your own over Christmas. Are we talking historically, Luke, or are we talking modern-day candles? Because there's a slight trick answer to this.
I was thinking modern-day candles, but we can go for both.
Well, the reason for saying that is if you wind the clock back a few hundred years when people made candles out of, do you know what?
Fat?
Yeah, it was pig fat, tallow. And therefore, the candles would have been made from an animal product, and the animals would have eaten plant matter in order to make the fat that went into being their body fat that then became the candle. And that's actually why rats used to love candles. Historically, if you read old John Mansfield books and things like that, you'll see that the rats gnawing on candles because they liked the fact they were made of fat. And because the pigs that they were made from would have eaten plant matter, the carbon in the candle wax would have come originally from the atmosphere because trees would have turned it into sugars and turned it into starches and celluloses and things that the animals would have eaten and then incorporated into their own body. So burning those candles isn't bad for the environment because basically it's carbon neutral in that regard, although I suspect there's a few partially burned hydrocarbons and I suspect Dave might have a comment on that. Modern-day candles, though, are made, as you suggest, from paraffin wax. So these are fairly long chains of hydrocarbons. They're oil-based. Burning those, you're burning a fossil fuel, so they're not so good for the environment.
Okay, also, what sort of implications are they to a light bulb? So how many candles and how long you had to burn those for to equate to a light bulb?
Dave, do you know the relative comparison between a candle and a light bulb?
I'm not entirely sure. I do know that candles are very, very inefficient compared to a light bulb. They are running very cold. They're not completely burning. You get quite a lot of soot out the top of them. And really 99% of their energy is going into producing heat radiation and heating things up rather than actually producing the light which you actually want.
And also going back to the tallow point, I think we also... pigs aren't necessarily carbon neutral. Well, not carbon, but greenhouse gas neutral. They do produce a lot of methane, and that's a very powerful greenhouse gas. I think you might have to take that into account as well.
True, but I guess historically there wouldn't have been that many of them, so we probably wouldn't have had to worry too much, would we?
The other big environmental thing, which was a really major use of candles, especially the best quality ones, they were made from spermaceti, from sperm whales. They have a big sort of waxy, oily area in their heads, which they use to focus sound waves for their sonar. And really quite a lot of the best quality candles were made for those and did hideous things to the whale stocks.
I think you've got something ridiculous like 10 tonnes of oil came from a single sperm whale weighing between, is it 30 tonnes, Helen, a sperm whale?
I think so, yeah, absolutely. And I can't agree more that making candles out of whales is a really bad idea.
Maybe you can help out Martin Schaefer on our Facebook page, Dave, and he's saying, on the subject of candles, and thank you, Luke, for that great question, why does the wick of a burning candle only smoulder at its end but shortens after you've blown it out?
The way a candle works is you've got a kind of bath of molten wax. This is pulled up the wick by surface tension, and then that evaporates. And when a candle's burning normal, it's this vaporized wax, which is combining with oxygen and burning away. The wick will stay there pretty much on its own and sit there. If you blow the candle out, you'll get a load of kind of smoke, and that's actually the wax vapor recondensing and forming little droplets of solid wax in the air. But the end of the wick can still carry on burning. It's still quite warm, and that will continue burning with oxygen. So that's actually the wick itself burning the string inside the wick, and that will kind of smoulder away for a bit, and also smoulder away a bit like any bit of wood which smoulders for a while and eventually go out. But it's not hot enough to reignite the wax.
Thank you, Dave. Hella Reid on that Facebook page, also on the subject of candles. What's the healthiest way to extinguish a Christmas candle? Dominic, any ideas?
I guess if you cover it, then it becomes smothered in carbon dioxide, and that means it's going to go out very quickly. And
what about the pinch technique? I suppose that's slightly unhealthy if you burn yourself in the process.
You want to be quite careful doing that, yes.
But actually probably healthy in terms of what's been given out, because the bad thing for you is if you have partially burnt things, you get carbon monoxides and nasty hydrocarbons and things. And so if you can get it going from burning cleanly to being out as soon as possible, that's probably the most healthy. But I wouldn't, unless you're doing it every day all the time, I don't think it's going to kill you.
Well, here's something that's very healthy for your brain. Tell us about what you have in mind for kitchen science. This is an all-time favourite experiment. Off you go, Dave. This
is one of my favourites. It's so simple and so surprising. All you need is an oven shelf, or in fact, a metal coat hanger, just something kind of metal which you'll kind of vibrate when you hit it, and a piece of string. And all I want you to do is tie the piece of string onto the oven shelf or onto the coat hanger. So you've got it hanging off there, hanging free. And I just want you to tap it with something, a pencil or something like that, see what sound it makes, and then wrap the string around your finger, bend your finger over so you've got your knuckle, then push that knuckle just onto the bone just in front of your ear, lean over so the metal thing isn't touching anything, then bash it again.
It is really smashing. We'll actually be coming back to that shortly in the programme, and you can find out what other people are hearing when they have a go. Now, talking of sort of exciting science, Helen, what have you been looking at in the news this week for us?
Christmas is coming, as we've all noticed, and I suspect that there'll be lots of movies watched over the Christmas period. And perhaps one of your favourites, certainly one of mine, is Finding Nemo. And the fact is that now scientists have uncovered the fact that 1 in 6 species featured in the Finding Nemo movie are at risk of disappearing from the oceans, and that's due mainly to overfishing. So really, the chances are that you're not going to find Nemo if you actually went and looked for him yourself. A research team from Simon Fraser University and from the World Conservation Union, the IUCN, they examined the extinction risk facing over 1,500 marine species. OK, so there weren't 1,500 species in Finding Nemo. What they did was they took the families that you can see on screen and examined all the species in those families. And that included things like hammerhead sharks, sea turtles, pelicans, pufferfish, eagle rays and seahorses. Hooray for seahorses. So the information they gathered came from the IUCN's Red List assessments, and this essentially ranks the extinction risk ranging from critically endangered through endangered, vulnerable and near threatened of various different species. And these categories are all based on a very detailed set of standards against which the size of populations and the changes they've undergone are gauged. And if there's not enough information, then these factors, then basically a species is labelled as data deficient. What they found was that 12 to 35% of the species they looked at were considered to be threatened with extinction. That's ranging from critically endangered through to vulnerable. And to be honest, the point of this study isn't really to see if Hollywood has got anything to say about extinction in the oceans. It's more about assessing how well these famous, charismatic species that are getting, attention from us, how are they getting on, both in terms of their status in the wild and our efforts to protect them. Because frankly, if we can't figure out conserving these glamorous animals like sharks and turtles, what hope is there for the lesser-known species that don't make it onto the silver screen and that few of us have actually heard of?
Isn't it quite good that Hollywood does champion some of these species, because then at least people have heard of them and then they feel they have a sort of stake in their welfare, really.
Absolutely. I do. I love the fact that even any vaguely recognisable marine species makes itself that well known. But the point they're making is there's an awful lot that we don't really hear about, and how are these famous species getting on? And in fact, not so well, it seems. I mean, there are actually a real lack of binding conservation steps being taken for these charismatic species that we've heard of. For example, on things like the Convention on Trade, International Trade in Endangered Species, there are lots of species of sharks that, for example, aren't being managed at a global scale, which is what we need, because they're seeing these global problems and we need global efforts to try and protect them. But I have to say, it's not all doom and gloom. Public awareness, although it doesn't always come hand in hand with conservation. One problem was when Finding Nemo came out, people rushed out to go and buy their own Nemos, sometimes taken unsustainably from the oceans, and then a bunch of other people, kids mostly, flushed their Nemos down the toilet to set them free. So that wasn't great. But, on the whole, we are seeing, as you say, Chris, we are seeing more of the oceans in the media. We're seeing them on the screen. We're seeing them on cartoons and so on. And that's helping to spread the word of some place that otherwise is out of sight and out of mind.
One important thing, because it's very easy to focus on, I suppose, the exotic things, but there are also more, I hate to use the word mundane, but there are more sort of everyday type fish that we just exploit for food, like mackerel and herring and things. There were some fishermen who got themselves in hot water in Shetland recently for overfishing their quotas. How do they set those quotas? So when the government or the EU say, right, you're going to be allowed to fish X amount out of the ocean, what science is informing how they set those limits?
It's a very good question. In fact, a new set of quotas is just coming out for the EU. It's the whole way that the fishery is managed, and it's looking like what the fishermen are now going to get is fewer days at sea with slightly larger quotas. It should be based on science. It begins with science, it ends up with a policy, and there's a long way in between those two things. But if we're looking just at the science, it's about how many fish are in the ocean still, how they're reproducing, how many young there are. It's understanding how the population is doing, essentially. How are they dealing with us taking a whole bunch of them out and replacing themselves. So to get that information, you need to do stock assessments. You can do that all sorts of ways, by counting the fish we do fish, by actually sending down sonar. And there's ways of actually sort of imaging and figuring out how many fish there are in the oceans. We can't count them all. We've got to make estimates and then sort of add it up from small samples here and there. It's not perfect, but it's what we've got. And it's not always legal, and people go and break those quotas, and that's what's been happening in Shetland.
Thank you, Helen. Well, one of the other things we're asking our crew to do this week is to come up with the piece of tech that they would most like to see under their Christmas tree on Christmas Day. Dominic, you're up first. So what's your ideal dream tech Christmas present?
This may sound like a bit of a cliche, but I think for any astronomer to have a time machine...
So your own black hole?
Well, a black hole might be quite fun as well. I think a time machine to be able to sit at a telescope and to see how objects change over the course of millions of years would be really incredible. Because a problem that astronomers have, they get to study these absolutely huge, awe-inspiring objects that are often incredibly violent in ways which are quite hard to comprehend, forming stars and supernova explosions and so on. But because these objects, galaxies, are so large, it might take light 10,000 years to travel from one side of a galaxy to another, and that galaxy isn't going to significantly change shape or evolve before your eyes in a human lifetime. So I think to be able to sit at your telescope and fast forward a million years into the future and actually see these things colliding and forming stars and doing all these processes that we theorise they undergo would be really quite awe-inspiring.
What would you like to see under your Christmas tree this year, apart from a massive cheque to help offset the balance of the deficit in the economy? If you have a scientific wish list, then let us know, or any science questions. It's The Naked Scientists with Chris, Dave, Helen and Dominic. We're answering your science questions for our Christmas special. Email chris@thenakedscientist.com, and our Twitter name is @nakedscientists. And still sticking with the questions, Daniel is there. Hello, Daniel.
Yes, sir. How you doing?
Very good, thank you. What can we do for you?
Whenever I get in the shower and I notice I've already got the temp turned all the way up to full blast, it's hot. But when I first get in, the smallest droplets that I feel, as soon as they, the kind of ones that kind of spray off, they seem to hit my skin, and the first feeling I get is not that of hot, but it's actually of a rather cold temperature. And I was wondering exactly what causes this.
Well, I think what's probably happening in your shower is that although the water leaves the tap, or at least the shower head, nice and hot, the fine spray is caused by two things happening. One, some of the droplets will break up as they pass through the air at high speed. And number two, a lot of the spray is because the droplets hit something like the wall or the sides of the shower, and then they split up into lots of smaller droplets and fly onto you. But the point is that they've had contact with something which was a cold surface, and so they've lost a lot of their energy to the cold surface, and they've also, as they've gone through the air, because they have a high surface area to volume ratio, lost more energy to the air, so they tend to feel cooler. I think that's probably the most likely reason why the fine misty spray feels cooler than the big droplets, which have got more energy in them because they've got a bigger volume relative to their surface area, so they're losing less of their energy less quickly. Would you agree, Dave?
Yeah, and I think the other really big thing is just evaporation. Water evaporates, and actually you have a bowl of water sitting at room temperature, and because all the hot water molecules evaporate off the top, what's left actually gets cooler than room temperature, and these tiny particles have got a huge area to evaporate from, so even just from the spray head down to your body, they've got enough time to cool down below your body temperature.
I think the other thing that will be going on is that when you're standing in the bathroom, the air will be mostly still and you'll have a warm layer of air next to your skin. But when you turn the shower on, it will start stirring that air around and blowing that warm layer of air off your skin, and cold air will come in instead.
Thank you, guys. Got a question for you, Helen. Peter sent this one in earlier.
Hi, my name is Peter and I'm calling from Dortmund, Germany. I'd like to know which color a dead chameleon has. Does it keep its last shade, or is there some kind of neutral skin color?
Chameleons are fantastic. If you've ever seen a chameleon, especially in the wild, they are fabulous things. Especially, I've seen the biggest chameleon in the world and one of the smallest chameleons in the world when I was in Madagascar. The biggest ones are sort of a good foot long, called Parsons chameleons. They're huge, great big green things usually. And pygmy chameleons, which are the sort of size of, they'd sit quite happily on your little finger. They do a great job of just making themselves look like leaves. But actually, an interesting point about chameleons and their colours is that we use the word chameleon to mean camouflage and to mean hiding away. But this is a bit of a myth. In fact, recently scientists and researchers figured out that actually chameleons really use colour to show off and to talk to each other. So males will fight each other and they will use bright colours to communicate. Females and males will interact using colour, and that the hiding away thing and camouflaging themselves against their background actually isn't the main reason that chameleons have colour. They do have colour and they can make themselves look very bright by having different pigments in their skin in different layers of reds and yellows, blues, whites, and there's a neural signal that will cause those cells to essentially expand and contract and reveal different combinations of colours, and then that's how they get these colorations. So to answer your question, when they're dead, I mean, I haven't seen a dead one myself, and I asked my friends who work in Madagascar, which is where there are lots of chameleons, and they hadn't seen a dead one either. I can only assume that given it's a nerve control that gives these bright colours, that once those nerves stop, I would have thought it would relax back to the sort of the relaxed, unexcited state.
Pale
so
green.
generally, sort of whatever their browny, quite drab coloration that would sort of generally just blend them in and not shout out, "Hey, look at me, I'm a fantastic male."
Fantastically dead chameleon.
Exactly.
Thanks, Helen. Now, this one is an interesting one. This has been sent in by Steve earlier.
Dear Naked Scientists, I have a question about tooth fillings. Why is it that when one of my older silver tooth fillings comes into contact with metal stuck on food, such as a gum wrapper or aluminum foil, I get intense pain? My guess is that the two different types of metal in saliva create a small electrical current. If so, how does this happen? Thanks for a great show.
One of the things which could certainly be happening when you touch two metals together in your mouth, where there's a load of electrolytes going on, some chemistry can happen at the same time, is you've essentially made a battery. If you have two metals with different reactivities, basically the most reactive one will tend to form ions. So if you've got aluminium foil, that's quite a reactive metal, so that will form Al3+ ions, so that will dissolve. And the least reactive metal will have a load of extra electrons given to it, and then it will somehow get rid of those electrons. So either it will, if there's any dissolved things in the around the place, dissolved metals, they will deposit on the surface, or there could be some other electrochemistry going on. And my only guess at what's going on in your filling is that some of that electrochemistry is happening near the nerve of in your tooth, and it's annoying the nerve and causing you some pain.
Either because it's passing some of the electrons that are resulting from the battery you've made in your tooth filling into the nerve and directly stimulating it, or perhaps it's making some gas locally by reducing some hydrogen ions in the solution in the plasma, and that's making some hydrogen gas, which is actually increasing the pressure inside the tooth, and that could put pressure on the nerve and make you feel like you've got toothache, which is, again, pressure inside a tooth because bacteria are irritating a nerve.
Or even just produce something kind of slightly poisonous, which just directly chemically annoys the nerve.
We're also taking a look at what's hot in the news, scientifically speaking, this week as we run up to Christmas. And Dominic, you've had your eye on Christmas with a sort of astronomy theme. Tell us about this one.
That's right. This is something of a Christmas firework left over from last year. It's a gamma ray burster that was observed at about dinner time in the UK on Christmas Day last year. Now, a gamma ray burster is a burst of radiation similar to what you would find in a nuclear reactor, but thankfully very much weaker, and coming out of a night sky. Now, these are normally very short events. Many of them last less than a couple of seconds, so they're very difficult to observe. But certainly even longer lasting events typically are over within a couple of minutes. This one, however, was really quite a surprise because the gamma ray particles carried on coming for about half an hour, and you could still actually see them a bit after half an hour, up to about 45 minutes. So it's quite a challenge to explain what this could have been that was so energetic that it was producing these high energy gamma rays for such a long, prolonged period. Now, we have various ideas about what causes most conventional gamma ray bursts. We think the short ones are probably caused by neutron stars colliding with one another, and you have a tremendous release of gravitational energy as those two stars combine and form a black hole, and that energy is released as gamma rays over a period of about 2 seconds, because these things are so small they can combine very quickly. We think the longer bursts are caused by supernovae at the ends of the lives of very massive stars, but even they will only last for a couple of minutes. So how could you possibly prolong this process to last for half an hour?
So what do scientists think could have done that?
Well, in Nature earlier this month, there were 2 papers that present 2 actually very different theories for what this could have been. One of the theories is that this was a neutron star colliding not with another neutron star, but with a massive star just as it was about to go supernova. And that's actually quite a realistic scenario, because as a star is about to go supernova, it will expand. And if it's got a neutron star in a close orbit around it, it will then engulf that neutron star, and the neutron star will get pulled in towards that star.
So it's one star about to blow itself up, eating another star at the same time. Does this then trigger a cataclysmic reaction then?
Well, the star was about to go supernova anyway, so that certainly pushes it over the edge into going supernova. So you have the 2 types of gamma ray burst happening back to back, and that could perhaps lead to quite a prolonged emission of gamma rays. Now, the other model is a complete contrast to that. It's saying perhaps this was quite a small event quite nearby in our own galaxy. Perhaps it was a neutron star with a rocky asteroid about the size of the asteroid Ceres in the solar system that came too close to this neutron star, and it was broken up by the tidal gravitational forces around this neutron star into lots of little pieces. And these pieces fell in one by one over the course of about half an hour, leading to lots of very weak gamma ray bursts that we saw as this continuous spread of gamma rays. Now, both of those models actually turn out to fit the observations pretty well. But I think that the point this does bring home is that probably there's not any one mechanism which is responsible for all gamma ray bursters. These are probably caused by a huge range of phenomena, and they just happen to look quite similar when we observe them.
Brilliant. Dominic, thank you very much. So, Dave, what have you been looking at in the news this week?
I saw an incredible story. A camera has been built which is capable of taking 1 trillion frames per second.
OK, that's pretty fast. What's the next best? Or next fastest?
There are certainly cameras around which will take hundreds of thousands of frames a second, but I don't think this fast. You've probably tried slowing films down yourself. Eventually they get jerky, in fact really quite quickly. It's because your camera only records maybe 15 or 30 frames a second. And as you slow it down, there's no information between those frames, so it becomes really jerky. But Professor Ramesh Rashkar at the Media Lab at MIT has created a camera which will do 1 trillion frames per second.
What technically is the problem that you have to solve in order to make a very fast camera then? Why is it difficult?
To do it properly, you'd have a sensor which resets itself 1 trillion times a second, and just electronics can't do that.
So it's a technological problem?
It's just physically very, very difficult to do. The way they did it was with something called a streak camera. Now, this only looks at one line of the image at a time, so it's not looking at the whole picture. And they project this line onto a screen, and the screen converts this light signal into a signal of free electrons, and then these are accelerated along a vacuum tube towards a detector at the end of a tube. This beam of electrons can then be deflected incredibly quickly up across the sensor. So you end up with the bottom of the sensor detecting what hit it at the beginning of your recording time, and the top of the sensor is recording what happens at the end. So you can deflect these so fast you can get this trillion frames a second.
And how do you build up one line of an image into the complete image?
Well, this is where they're cheating slightly, and it's not really a proper trillion frames a second video camera. They have to then do the same thing again for another line and again for another line, so maybe 500 times to get a full, fairly low-resolution image.
But you recompile all of those things, stitch them all together in time, and you see the complete image as it would have been if you'd seen it in the full dimension rather than just as a line.
That's right. So you are constrained to things which you can repeat exactly again and again and again.
What does it look like when you see these images then?
They're absolutely incredible. They've got a very, very short laser pulse, about 1 millimetre long, and you can see this moving across the screen, a kind of slow, as you'd move your hand across a table or something, very slowly.
You actually see a wave of light going along.
You can see a pulse of light moving across, and then the really incredible thing is if you set up a mirror, you see the pulse go up to the mirror, then it bounces off the mirror, and you can see the reflected light coming off in another direction.
That's amazing. OK, let's go up a gear then. What about if you do these clever experiments where you put light through two different parallel slits? You know what I'm going to say? When you put light through one slit and then you've got another slit next to it, and you get this interference pattern where the light waves interact with each other. If you watch the photons coming through, then they just make two spots of light. If you don't watch them, you get rings and interference patterns. What would happen if you did that experiment with this?
Well, this isn't actually looking at the light as it's travelling along. What you're actually seeing is scattered light. The light hits something and bounces off. So if it's hitting some dust in the air or it's hitting a tabletop or something, you are seeing that pulse moving along. And this thing with reflections is why it could be really, really powerful. Because if you had some complex object, they did it with a big pile of crystals, it's almost impossible to see inside that because the reflections from the surface completely mask what's going on deeper inside. But if you watch it with this camera, they've actually got a video of this, you see the light going in and then you see the reflections coming out from near the surface, and then you see them later reflections, and you see the kind of whole thing sparkles for about 5 or 6 seconds slowed down. And so if you did lots of very clever maths to that and probably illuminated it from different directions, you could actually build up a picture of what was inside that crystal structure, or possibly even inside the body, because the body is actually relatively transparent. It's just it scatters light really well. And if you could separate when the light came out of your body, and you do a lot of hard maths, you can actually work out pictures of inside your body invisible light without cutting yourself open, and that could be an incredibly powerful technique.
Or resorting to other forms of radiation, which could be harmful to do it.
Both harmful and don't give you the same information, because there are various diseases and things which you can identify with visible light, but you couldn't do with ultrasound or X-rays. And now with a look at what else has been sparking scientific interest around the globe, here's Mira Senthalingam with the Naked Science Newsflash.
The African lungfish uses its fins to walk rather than swim underwater. Publishing in the journal PNAS, Heather King from the University of Chicago monitored the movements of lungfish in tanks of water and found them using their pelvic fins as hind legs to walk along the bottom of the tank. The findings suggest that walking may have evolved underwater rather than on land.
This is evidence to support the idea that perhaps walking evolved before feet evolved, or digits, or terrestriality. In this lineage, lobed fin fishes to which tetrapods belong. And of course, we are tetrapods. Every land animal with a backbone and 4 limbs is a tetrapod. So that's why lungfish are important to look at, because they're one of the last closest relatives of the tetrapods that's still alive.
The smallest steam engine in the world has been developed by scientists at the University of Stuttgart. Using a single colloidal particle called melamine, thousandths of a millimetre in size, submerged in an equally small chamber of water, Clemens Beschinger used a laser to trap the particle and varied the laser's intensity to either restrict or free the particle, resembling the compression and expansion seen in a large-scale steam engine. A second laser was used to heat and cool the water bath.
If we change the intensity of the heating and compression expansion laser beams in the right way, we can then make this engine to work. And the surprising result is that if you tune the parameters correctly, then the efficiency of such a small steam engine, although it stutters, although it doesn't run as smoothly as its macroscopic counterpart, can be as large as that of a macroscopic steam engine.
Birds living in cities produce higher-pitched sounds than those living in more rural environments. It's long been known that urban birds produce a different song to those in the countryside, but the reasons why have been subject to speculation. But now, recording and monitoring the songs of great tits in and around the city of Sheffield, Emily Mockford from the University of Aberystwyth found that birds within the city produce sounds of a much higher pitch, enabling the sounds to travel further and echo less off surrounding buildings.
The architecture of a city is in fact changing the way that sound travels through the environment, and it will affect how birdsong travels through the environment as well. We need to think about the way we build our cities and the way the wildlife has to adapt around us. It's not actually the noise that we're making, but it's actually the physical soundscape that we're creating as well that they have to adapt around. It is the larger cities that will have this problem because it's these massive reflective surfaces and urban canyons and open spaces that are changing the way that sound travels.
Mosquitoes release droplets of fluid to keep themselves cool whilst feeding. Scientists have often wondered how cold-blooded insects such as mosquitoes prevent themselves overheating when consuming hot blood from a human. Using thermal cameras to monitor mosquitoes during a meal, Claudio Lazzari's team from the University of Tours in France noticed that as they feed, the insects exude droplets of fluid to cool their bodies down to ambient temperatures.
We have seen that at the beginning the mosquito warms up, and very soon during the feeding process they start emitting a droplet of urine that they keep attached to their body, and at that moment the temperature of the mosquito's body starts to decrease because of the evaporation of this fluid. So the evaporation produces a loss of heat in the mosquito's body.
The work could be used to control mosquito populations in the future and is published this week in the journal Current Biology.
And as usual, you'll find more science news along with references on our website at thenakedscientist.com/news.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris, Dominic, Dave and Helen. We have a very special kitchen science experiment running. Dave, can you just give us a quick roundup on what you want people to do?
Basically, all I want you to do is grab an oven shelf or any kind of bit of metal, made out of wire, hang it on a piece of string. First, hit it with a pen or something, see what it sounds like. Then wrap the string around your finger, bend your finger over to make a knuckle, touch the knuckle just in front of your ear, lean forward so there's nothing touching anything else. Then bash it again and tell us what it sounds like.
Email chris@thenakedscientist.com, or you can tweet @nakedscientist. And Dave, what are you praying for under the Christmas tree this year yourself?
What I'd really like is an incredibly strong piece of string.
Some people want for a time machine, and you're asking for string.
Well, I would really like to go to space, but I think space rockets sound a bit dodgy. You're essentially sitting on a huge, great piece of explosive, and also incredibly energy intensive because in order to get the force to go upwards, they've got to get it by throwing fuel down, and the further up you go, the more fuel you've got to carry, and the more fuel you're carrying up, the more fuel you need, so they get to be immense and incredibly inefficient. So what you could do is build something called a space elevator, which is you get a geostationary satellite, a big heavy lump just outside geostationary orbit, and you just put a piece of string up to it, and then that string is in tension because the Earth is actually pulling that satellite round all the time, and you've got a great big long wire which you can climb up. The problem is there is no material that we can certainly produce at the moment which could possibly be strong enough. If you made it out of steel, it would have to be bigger than the Earth at the top to be able to support itself all the way down at the bottom. And so a piece of string which was strong enough to build a space elevator would be wonderful.
Thanks very much, Dave. So, Helen, carrying on with the theme of your dream tech on Christmas Day. What's yours?
Okay, so I would like to have a Babel fish that works underwater. So by that I mean the invention of the little tiny creature that you can stick in your ear and it will translate any language for you. And my particular desire will be to have one that will let me know what the fish are thinking, or if they're not thinking.
So the aquatic equivalent of Dr. Dolittle, really?
Well, yes, I guess I do want to basically talk to the fish. Oh, I just really want to listen in. I don't necessarily want to tell them anything. I would just want to know what they're thinking, because I think we could probably learn quite a lot if actually we understood more about how they perceive the world, what's going on around them, what's going on in there, basically. So a Babel fish that works underwater for all of the marine creatures, please. That would be lovely. Thank you.
Bob is on the lines in Hawthorne. Hello, Bob.
Hello.
Merry Christmas.
Merry Christmas to yourselves.
Off you go.
Okay, the problem is rainbows. I have been fortunate on a number of occasions to be fairly close to the end of a rainbow, and by that I mean probably 300 or 400 meters away, where you can see the actual end of the rainbow striking the ground and see the colours, and if you look through it at objects behind, you can see clearly the coloured lights are your side. This might relate to the angle of the sun forming a triangle with the object that's causing the prism effect, where the actual hitting of the ground point, because the actual rainbow seems to be close to half a circle. But the problem remains, why only one rainbow, and why does it appear to end there? Because you look at trees slightly higher up, you don't get the rainbow effect. Is it going beyond, or is it still in front of that tree? But it doesn't appear to be so.
Okay, the way you see a rainbow is every raindrop, when sunlight shines onto it, it actually produces a cone of rainbow. And if you look at that, if you actually look and project it, you see a cone projected from each individual raindrop. What that means is if you look at each raindrop from different angles, it looks different colours. So that if you're looking over to your right, low down, some of them will look red in one angle, a slightly different angle. You see them at a different angle, they look red, green or blue or different colours. And the same, because it's a cone, you get the same effect up above you and over to the left. So the whole rainbow ends up as this arch. How close it looks will essentially be to do with how dense those raindrops are. If you're in a kind of fairly light rain, then the amount of light reflected back to you per metre is quite small. So it will look like it's a long way away because there'll be hardly any coloured light coming to you from the nearest 100 metres, and you'll have to add up several hundred metres, maybe a kilometre, to produce enough for you to see the colour, so it will actually look a long way away. If you're in an incredibly heavy rainstorm, which I expect, which is probably what you saw it, then there might be so much light being reflected off the rain, which is really close to you, that actually most of that light is coming from 100 metres away. So it's actually in front of the building which you're seeing, or the tree which you're seeing behind it.
Dave, thank you very much, and I hope that answers your question. Bob, we've got one from Tim, who's in Essex. He's actually sent this one in.
It's Tim in Essex, and what I wanted to know was, is it dangerous to human health to wrap foods in aluminium foil, knowing that there might be a link between aluminium and Alzheimer's?
OK, thank you, Tim. The answer to this one is that although there is a link between Alzheimer's and aluminium, in the sense that if you look in the brains of people who have Alzheimer's disease, you find these build-ups of protein. They're called Alzheimer plaques or beta-amyloid plaques, and if you look inside those, you can find aluminium ions there. It's not clear whether the aluminium goes there because the plaque is there and therefore the brain is already abnormal, or whether the aluminium helps to start the process off in the first place. What we know is that when you cook things in aluminium foil or in aluminium pans, because aluminium is a very reactive metal, the surface of the metal is covered in a very thin layer of an oxide, aluminium oxide, and this actually protects the metal from the atmosphere. That's why aluminium doesn't rust like iron does. It's fairly well protected by that oxide layer, and this means that the aluminium can't actually get into the food in any appreciable amount. The exception to this is if you cook very, very acidic foods in your aluminium pot, and a good example of this is rhubarb. Rhubarb is extremely acidic, and if you make a rhubarb crumble in an aluminium cooking pan, you will find that it needs virtually no cleaning afterwards, because the acid attacks the oxide layer and can liberate a small amount of aluminium from the pan, and this can get into the food. Whether that will then produce Alzheimer's disease subsequently is a bone of contention, but people say you're advised not to cook very acidic foods in aluminium-rich cooking materials and utensils, because there is a small risk that you might get aluminium in the food and it could therefore have health consequences. Some of the interpretation is based on what happened to people in, I think it was it Castleford in Devon, Dave, was the time when they accidentally dumped a whole lot of aluminium in a water settling tank, because aluminium is used in, say, swimming pools and at sewage works as a flocculant. It causes small particles to clump together. And they accidentally put some aluminium in a tank that people were going to drink from rather than a tank they wanted to settle out. And so people were receiving a very high dose of aluminium, and there were some alleged connections with Alzheimer-type changes in people subsequently, but we don't know if those people were just going to get Alzheimer's anyway. So it's a good question. It's open to debate. So don't cook acidy things in those sorts of tins. That would be my advice anyway. Dominic, there's one here from Hong who has actually said, since the moon is moving away from the Earth, how strong a cable would we need to tie the moon down and stop it getting away?
I guess we might need Dave's special string for this. One problem that you would have is the fact that the moon goes around the Earth every 29 days, and so you'd need some quite good bearings on this string to carry it around the moon's orbit over the Earth. And that would be especially difficult because the moon doesn't trace out the same path over the Earth each time it orbits. So you'd need some kind of travelling system to hold onto the end of this piece of string. Certainly people have done the calculation for geosynchronous satellites to make space elevators. And people have worked out that even Spider's thread, which is the strongest string that we know of, is not strong enough to support its own weight to travel up to a geosynchronous satellite. To go up to the moon, you'd need something considerably stronger than that. So I think you'd be in the realm of Dave's string for that.
Because the moon is actually, we're seeing it going further away by a couple of centimetres every year. And in the process, it's basically we're giving the moon from Earth's spin energy, so the moon is speeding up, which is why it's departing, isn't it? Because it's basically the moon slightly lags the Earth in terms of the Earth's turn, which is why we're basically giving energy to the moon, because it's basically heaping up water on the Earth's surface. That's
right. The moon is triggering the tides on the Earth, and in the process of triggering those tides, because the Earth is spinning, it's putting a force back on the moon, which is spinning up the moon's orbit and will eventually mean that the moon might leave the Earth's orbit altogether.
Thanks, Dominic. Helen, just to pick you up on your chameleon thing, or to add some extra information here, Helen McLennan has got in touch and she said, I thought I'd let you know the colour of a dead chameleon. Unfortunately, my nosy bee panther chameleon died earlier in the year. He was usually a bright coloured chameleon, blue, white, green and yellow, but when he passed away, he went a very dark black or brown colour, and from my understanding, this is the normal colour of a dead chameleon.
Well, there you go. A nosy bay, that means large island in Malagasy, so I assume it was a Malagasy chameleon she had.
Okay.
Yeah.
Now, a remarkable paper was published in the journal Science recently. An international team, led by Roy Wigelius from the University of Manchester, has developed a new technique that reveals the colour and even the chemistry of fossil birds. And these are birds that are more than 100 million years old. The team used high-powered X-rays to detect trace metals in the fossils and related these to melanin pigments that are in modern birds. And unlike other methods, this process doesn't involve damaging the fossils. Planet Earth podcast presenter Richard Hollingham went to meet Roy to see the fossils for himself.
This is a 50 million year old fossil feather.
And it's almost perfect. Very fine. Wispy strands.
This is the kind of thing that we call exceptional preservation. You can see the central shaft, and we can see the barbs that fan out from either side. The preservation is absolutely splendid.
So this is 50 million years old.
That's right.
And you can tell from a fossil, with your technique, the chemistry, and from that, perhaps the colour of it?
That's exactly right. We know that the pigments in our hair and skin bind up with certain metals: iron, calcium, zinc, and copper. Copper is part of the enzyme that actually makes the pigment in our hair and skin and in bird feathers. So we thought maybe by mapping the trace metals we could see if there's some kind of information about coloration. Indeed, maybe the color that you're seeing, this preserved color, maybe that traces
that's
back.
That's real.
Yeah, maybe that's real. And indeed what we found is at the base of this feather there are higher concentrations of copper than anywhere else in the sample, much higher than in the sedimentary rock and much higher than in the top portion of the feather. The other thing we're able to do using X-rays, not just map the copper, but also get the details of how the copper is chemically bound. What elements surround it? In other words, does it look like an organic compound or is it a purely inorganic compound? And the thing that we found absolutely blew me away. The copper chemistry in the base of this feather is nearly identical to the copper chemistry in melanin sampled from existing organisms. And so maybe we should go to the other specimen, which is perhaps a bit more exciting.
It's very well wrapped in bubble wrap and then tissue paper. Just pull back the tissue paper. That is incredible. I suppose it's the size of a large crow that's been flattened.
Welcome to our 120 million year old roadkill. What's amazing about it is that this is the first documented bird with a beak.
Oh, yes. And again on here, you've got colour. You've got much darker wings than the bones in here, which are almost a bone colour, even though this is a fossil. But again, how do you know these colours are real?
What you can see here is that in the neck region and around the body, there's this very, very dark coloration.
Almost black.
Yeah, that's right. Almost like carbon black. And if you look at the flight feathers, which are kind of splayed around to either side of the body, the top has this relatively dark black coloration. And then as we move away in the flight feathers and go further and further away from the body, they get lighter and lighter in color. And what we find is that in the neck region and body region, there's very, very high concentrations of copper. We've also done infrared analyses on these regions, and the infrared spectra look exactly the same as modern-day melanin. We've done structural work. All of this information sits together to tell us that the downy body feathers on this bird were very, very rich in this dark black eumelanin pigment.
So this was some sort of black bird?
That's right. That's exactly right. It's unambiguously, non-destructively, and over the whole organism, we can pull out patterns without having to destroy anything.
Now, I mean, this is fascinating. Is this useful?
There are aspects of behavior and evolution and ecology that were inaccessible to paleontologists until they could start to see color patterning. That tells us an awful lot about camouflage, sexual display, a whole different range of behaviors which you really can't get any kind of clue from just bone material. So it's the soft tissue. So for the paleontologists, it's one of the reasons why they're so interested in this. This really might be able to tell them something about behavior. These trace metals contribute to biochemical pathways. They're still present. We know we can map them. And I think this gives us hope that things besides pigmentation actually become available to us as we study ancient life.
Roy Rogelius from the University of Manchester. He was talking with Richard Hollingham about the colours of fossil birds. And you can find more Planet Earth online resources by visiting thenakedscientist.com/Planet Earth. A little bit of feedback. Ralph in Stamford's got an interesting question for you, Dave. He says, smoke from a blown-out candle can be reignited, so why wouldn't a snuffed candle pop back into life?
Essentially, the wick just isn't hot enough to reignite that wax, because you actually need to get the wax hotter than the wick needs to smoulder. So it just isn't hot enough to reignite the wax vapour. Terrific.
Here is one from Nick.
Hi, I'm Nick. I'm calling from South Africa. And I'd like to find out if antiperspirant would cause one to perspire in a different part of your body.
The answer is the way that antiperspirant deodorants work, most of them are spray-ons, some roll-ons. They tend to contain a lot of zirconium, aluminium zirconium salts and chlorohydrate salts. The way they work is that you rub them on your skin. They form a sort of layer on the surface of the skin, and wherever they come into contact with water from your own body, in other words, where there's a pore linked to a sweat gland under the skin, they soak up the water and then they form a little plug of almost like gel inside the sweat gland, stopping any more water coming out. And if you therefore stop the water coming out, then the skin surface becomes drier. And the reason that we want to make the skin surface drier is if you have dead skin and water and a warm, wet place, you've got the perfect bacterial banquet. And it's the bacteria eating your dead skin, flourishing and thriving in this warm, damp environment that makes the whiff that we want to avoid. So we tend to apply the deodorants where we sweat the most, and you tend to sweat in those places for various reasons. One of them can be thermal. You do sweat to cool down, because when you sweat, you put a thin layer of water on the skin surface. We all know that. But what the water is doing is exploiting an effect called the latent heat of vaporization. In order for the water to go from a liquid into a gas, it has to rob extra energy from the skin surface to break the molecules apart, because they're all sticking together. And to separate out as a gas, then it needs extra energy to do that. And so when you've got the water on the skin surface, it's taking the extra energy away, and that cools you down very efficiently. That's why we sweat. But sweating is also under the control of something called the sympathetic nervous system. And that means that it's under the control of a part of your nervous system that you activate when you're worried about things. So people can also break into a sweat when they're very, very panicky, panic-stricken, anticipating having to run away very fast and things like that. And so as a result of that, you can also sweat everywhere on your body for a variety of non-thermal reasons. So just putting on antiperspirant deodorant won't necessarily affect the rate of sweating on other bits of the body, because if you're doing a stressful job, you might just sweat elsewhere.
But I guess if you're sweating for thermal reasons, then you're going to have less skin to lose the heat from, so the rest of you's going to be slightly hotter, so you might sweat a bit more everywhere else.
I would say, though, and I take your point, but I would say the skin area that you're applying the antiperspirant to is such a tiny fraction compared with the whole of the rest of your body, it probably is going to make almost zero difference, actually. Now, I want to warn you that what is coming up next may cause offence. Only joking. This is very, very humorous, not to be taken too seriously. Christmas is a time when you indulge in foods that we wouldn't maybe touch throughout the rest of the year. And we're talking here about Brussels sprouts, of course. There's an effect that you may be familiar with, and Sarah Castor-Perry is here to explain why they do what they do.
Every Christmas, one vegetable divides opinion: Brussels sprouts. Some of us love them, some of us hate them. But eating them can have some embarrassing consequences. Sprouts aren't the only thing that causes gas to build up in our intestines. Baked beans are notorious in this department too. But what actually is flatulence? Well, some of it is caused by swallowed air. We all swallow air when we eat and drink, but the worst offenders are gum chewers. Some of this swallowed air comes back up again as a burp, but any that doesn't can pass through the digestive tract and emerge again at the other end in the usual tuneful fashion. But most of the gas that ends up as flatulence is actually formed fresh inside our intestines by the colonies of bacteria that live there as a normal part of their microbial metabolism. They pump out variable volumes of nitrogen, methane, carbon dioxide and hydrogen. These are thankfully all odourless and largely harmless gases, although hydrogen and methane are quite combustible, as some party pranksters armed with a lighter and a convenient episode of wind will attest to. Unfortunately, some of the other gaseous products of bacterial digestion are much less easy on the olfactory system. Hydrogen sulfide reeks of rotten eggs, and methyl mercaptan, which stinks of mouldy cabbages, is the same stuff that's deployed by skunks as part of their repellent arsenal. But why are some foods far more fartogenic than others? And why does the bouquet of some airborne toxic events place them on the cusp of being classified as chemical weapons? As a rule, foods that trigger flatulence are those that can't be completely broken down in the stomach or small intestine. This means that partially digested foodstuffs then make their way into the colon, where they can feed a large bowel bacterial banquet with predictable odoriferous effects. And this is where the sprouts come in. Sprouts, along with onions, beans and dairy products, are hard to digest in the stomach and small intestine because our bodies can't produce the enzymes needed to break down some of the chemical components they contain. The main culprit in sprouts is a complex sugar called raffinose, which is also found in cabbage, broccoli, cauliflower, kale, and in fact all members of the Brassica family of vegetables. Raffinose is broken down by an enzyme called alpha-galactosidase, but as we don't make this enzyme in our guts, the raffinose, together with other complex sugars like the inulin, which is present in beans, arrive in the large intestine. Some of the bowel bacteria are armed with the necessary chemical knives and forks to break these sugars down, but in the process they churn out hydrogen, methane and carbon dioxide. So that's why sprouts make you produce gas, but why the particularly pungent smell that you often get as an unwelcome addition to the Christmas table? Well, one thing that all brassicas also have in common is that they're full of sulfur-containing defensive chemicals. They're there to deter animals from feeding on their leaves and are also what cause the strong and sometimes bitter flavours of these vegetables that put some people off eating them altogether. And it's these sulfur-containing chemicals that the bacteria turn into hydrogen sulfide and methyl mercaptan. Added in small amounts to the bulky sugar-fuelled fart gas already being produced, these gases are offenders that can clear a room in seconds. But is there a way of solving the problem, apart from avoiding sprouts in the first place, of course? Unfortunately, some people are just more prone to producing their own airborne toxic events owing to the unique community of bacteria with which they're colonised. Some guts are just more fart-friendly, you could say. And if this is the case for you, then perhaps Buck Weimer of Pueblo, Colorado can help. He won an Ig Nobel Prize in 2001 for his invention of underwear that contains a removable filter to help soak up any nasty nifs. For those who don't like the sound of charcoal-stuffed pants, there are some enzyme-containing dietary supplements that can help break down the complex sugars, reducing the personal fart risk. But fart experts agree there is no surefire way to prevent those Brussels sprouts sounding a bum note on Boxing Day. Merry Christmas.
Thank you, Sarah. That was Sarah Costa-Perry. Those were her own sound effects. We've got a science scrapbook video of that. If you want to go and have a look at the animation of it too, it's at nakedscientist.com/scrapbook, and you can also find it on YouTube. Now, the moment we've all been waiting for, which is the answer to this kitchen science conundrum that Dave set this week. Dave?
Well, what I asked you to do was to take an oven shelf, hang it on a piece of string, which Helen has been doing very beautifully over there, and just have it hanging there normally, and then hit it with something. So I just hit it with a penknife, and you get that rather tinny noise. Now, what I want you to do, Helen, is to bend your finger over into a knuckle, and then point that knuckle onto the bone just in front of your ear.
Okay, so I've got the string wrapped around my finger. I've got the knuckle on my bone. Okay, go for it.
I'll hit it.
Oh, wow. Oh, my God. Keep going. It's like... I feel like I've stepped into a sort of resonant church or a chamber of some sort, and there's sort of a cacophony of different notes coming into my ear. It's not just one note, it's a whole load of different ones.
We did get one person who called in on this, is what she said.
Here we go.
That's pretty good, actually. Okay, so...
but we don't actually know her name, so whoever you were, thank you for doing the experiment. We apologise, we forgot your name.
Now, Helen's reaction is wonderful, but we thought we'd try and get it on so you guys can hear it at home. Makes rather better radio that way. So I'm hanging this on a BBC microphone. Don't tell the bosses. So it's just about hanging on the microphone, happily. Now, if Chris wants to turn that on. So if you remember the tinny noise it was making before, and I'm going to hit it. You get that incredibly deep. So it almost sounds like some kind of giant gong. Very, very deep and exciting.
And that's what people are actually hearing in their heads, isn't it? When they hear this?
Exactly what you hear in your head. It's incredible and so simple. So what's going on is the oven shelf is vibrating, and it's vibrating with lots of different pitches. So it's vibrating at high speeds, which you can hear when you hit it through the air, and for much lower speeds, lower pitches. The air, however, isn't very good at transferring those lower pitches, and the reason is it's that the vibration has got to get transferred into the air. Air is a fluid, a bit like water. So I've got a glass of water here, and if you try and make waves in water with your finger moving slowly, so to be like a low pitch, the water's got lots of time to get around your finger, and so you don't get very many waves. But now if I try and move it much faster, the water doesn't have time to get out of the way, and it piles up and produces waves and gets my script wet. And so the same thing happens with air. The air doesn't have time to get out of the way for the high-pitched noises, high-pitched vibrations, so it piles up and you produce sound waves through the air and you can hear them. whereas the low pitches you can't. But with a string, it's essentially a rigid body. It will transfer all different pitches just as well as each other, so you hear those low pitches which were there in the first place.
And it getting into your head via the knuckle, how's that work?
Essentially, your knuckle attaches into the bones, and your bones vibrate, and then your bones make your ears vibrate. And this is the reason why your voice sounds so different to you than to everyone else, because you're hearing the vibrations going straight from your throat through the bones up to your ears. So you generally hear yourselves much deeper, much more impressive kind of voice.
Which is why everyone hates themselves when they hear themselves on the radio, for example. They hate the way they sound, or on a recording of themselves, because that's what you really sound like compared with what you think you sound like.
Yes, because you sound much higher and much squeakier and much more strange.
Me personally, or everybody?
I expect everybody, really.
Dave, thank you very much. You can find out how to do that experiment on our website at nakedscientist.com/kitchen science. It's written up there, along with, I think, conservatively about 250 other experiments. We now also understand that it was Jean who kindly obliged with her oven shelf and did that experiment for us. Thank you. In a second, we'll find out about an optical illusion to do with your feet. That's coming up, but I just want to touch on this one, which I thought was terrific. And maybe you can help me out here, Helen, in about 1 minute, which is how long you've got to answer this. With the discovery of bioluminescence and fluorescent proteins, could we theoretically genetically engineer a reindeer so it could have a glowing green nose? What do you think?
Absolutely. You want to basically take the glowing gene from a jellyfish of some sort, and I'm sure there are some out there that grow red. Okay, red is a bit rare in the deep sea, but there are some fish, in fact, that produce red light. Take the gene that produces that light in those species in the deep and stick it in a reindeer's nose. We've done it with mice. We've made glowing green mice, so I don't see why we shouldn't be able to make a glowing red reindeer.
Yeah, because there's green fluorescent protein, which is in jellyfish, you're right, and then there's a tweak that scientists have made to make red fluorescent protein, so the green equivalent in red, so it could be expressed. I think there probably are gene sequences that could direct the gene to only turn on in the nose, so you probably could end up with...
I'm not saying we should
Rudolph.
direct our research money to such a frivolous event, but it might be quite fun.
Right, talking of hard questions to answer, and thank you for that one, Helen. Time for our question of the week, and it's Hannah Critchlow taking over from Diana O'Carroll this week with a long or far-fetched question, you could say.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week, things that seem far, far away.
Hello, Naked Scientists. My name is Chris Markley, and as you may have guessed, I have a question. When I lay down, my feet appear farther away from me compared to when I am standing up. I wear contacts during the day and glasses in the evening. Could this be a product of my corrective eyewear, or a manifestation of my brain due to different visual reference points? Thank you.
So what does make your feet seem so very far away when you're lying down? We posed this question to Dr. Rebecca Lawson from the School of Psychology at Liverpool University.
It seems unlikely that any effects of glasses or lenses would differ depending on whether you were standing or lying down. We do seem to overestimate vertical distances, particularly if we're, say, on top of a cliff looking down it. We overestimate and think that the height of the cliff is greater than if we were at the base of the same cliff looking upwards. And in fact, agoraphobics seem particularly prone to this overestimation. However, this effect goes in the opposite direction. So really, I don't have a good account of why Chris's feet seemed further away when he was lying down than standing. But I think that his question really nicely shows up the complexity of human distance estimation. Perhaps surprisingly, we still don't fully understand how we judge the size and distance of objects.
So it seems to be a bit of a medical mystery and a science quandary. Geezer comments on the forum that it's the same as the optical illusion that makes the moon look a lot bigger when it's close to the horizon. Except here, it seems to be the other way round. Mike S. postulates, again on the forum, that gravity might be to blame, stating that without gravity compressing your spine, your feet are further away when you are lying down. He does concede, however, that gravity probably wouldn't have such an effect to make a difference here. And it's clearly not something that everybody experiences. Over the last week, we've had an office full of naked scientists, all of us lying down on the floor, staring at our feet, and then popping up to stare at our feet once again. And we can't say that we experience this phenomenon. Moving on. Next week, do sunglasses increase your risk of getting sunburnt?
Hello, Naked Scientists. This is Michael Patella from Winston-Salem, North Carolina, USA. And my question is the following. If you're not wearing sunscreen, are you more likely to get sunburn while wearing sunglasses? Thank you for taking the time to address this question, and keep up the good work.
Send us your answers by emailing chris@thenakedscientist.com. You can write them on the forum at thenakedscientist.com/forum. You can Twitter @nakedscientists, or you can write on our Facebook page.
Thank you very much, Hannah Critchlow. Now, in the run-up to Christmas, we asked you this week via our Facebook page, is there anyone out there who would like to do something wild and wacky for the Naked Scientists for Christmas? And this man stepped up to the mark. Rishi, hello.
Hi,
welcome.
how are you doing?
Now, tell us a bit about you. You're Professor Carmadillo, so what do you do?
Well, I built it as a science...
Just step a little bit close to that microphone for us.
I built it as a mini musical lectures, so sort of short songs on science and scientific themes. For instance, if you go to our website, professorcarmadillo.com, I actually have a song about green fluorescent protein and a nice little video to go with it.
And this week you said that because it had been Higgs boson furore, you were going to do something on that ilk for us.
Yep, a Christmas carol song done to the lyrics of a Higgs boson theme.
OK, it takes a brave man to do this. He's going to play us out this week. Professor Carmadillo, please take it away.
It's beginning to look a lot like a Higgs boson, above 115 GeV, that the two experiments gave. Results that say the same, was greeted with a sigh of relief. It's beginning to look a lot like a Higgs boson, below 130 GeV. They looked at the decay when sigma 3 confident say it's here or it's just a dream. They cannot deny a sigma of 5 is what they most desire, but it's Christmas time, I hope they get to relax beside a fire. It's been a busy year for them after all. Let me take you back to the seminar on December the 13th. The whole world was waiting on the edges of their seat for the results of the CERN experiments to be revealed. I tuned into the CERN website to catch the video stream, and my jaw dropped agape at the sight that I would see. It's beginning to look a lot like Comic Sans on the presenter's screen. Fabiola, you may have fab results from your lab, but your font lacks credulity. It's beginning to look a lot like the Vicar particle, a Higgs boson described accurately. For instead of looking inside a large hadron collider, many find mass in church on Christmas Eve. They cannot deny a sigma of 5 is what they most desire, but it's Christmas time, I hope they get to relax beside a fire. It's beginning to look a lot like the Higgs boson, the particle that gave us mass. They're hiding away in mince pies and the cake you'll eat on Christmas Day. Yes, they're hiding away in the mince pies and the cake you'll eat on Christmas Day.
Professor Carmadillo, thank you very much to him with that wonderful rendition about the Higgs boson. Well, that's it for this week and for this year. Thank you very much for joining us on The Naked Scientist through 2011. We're back in 2012 with more science. Thank you very much for your support this year, and thank you to our wonderful team, including Tom Simpkins, Mira Senthalinga, Ben Vausler, Diana O'Carroll, Sarah Costa-Perry and Hannah Critchlow, who helped to make this week's programme. Do have a wonderful Christmas, a wonderful New Year. We're back at the beginning of January answering more of your science questions. Take care. Goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.